So, hello, Joseph. Okay, you went to Dr. Okran. Okay, me send you Dr. Denchi number one friend or whatever with you. Okay. Okay, so of course if you increase this, it will give you a better shape that will follow a gamma distribution. Is that okay? Now, so I can now check whether, in other words, I want to estimate the parameters. The parameters I'm expecting are the shape of 2 and a rate of 5. Is that okay? Alright, so I'm going to go back to my earlier sample of 20 because I want us to also have, I'll ask you a question on this, so let me see. Okay, so I call mom dot gamma and then I pass in this data. What do I expect? Okay, so it's the same. So it has a shape of 1.64 and then the rate is 4.179. Is everybody okay with it? Okay. What is the parameter? It's 2 and 5. Yeah, okay. So what I'm going to do is that I'm going to also increase the sample size. I want to even go here and name them. So I want to name this so that it will, when I display it, it will name them as shape and what? Rate. Is that okay? Alright, so if you do that, you need to oh sorry, I need to not tab, like I need to do names of tab as that, and then tab should rather be this, and then I call tab, right? Okay, so I need to do this such that when I display it, it will tell me that this is shape and this is, so it's the same thing. I haven't done anything to this and I can do it. So now shape, rate, and then we can compare with what we need to do. Sorry, what we are actually estimating. So let me go back to the edits that I did. So basically, whatever my alpha hat and beta hat, I put them together to become what? A vector. I name the vector, the objects within the vector, and then I return the vector. That's it. Yes, is everybody okay with this? Any question? Okay. Can we move on? If you are having issues, please let us know so that we address it before we move on. All right, so your own will be different because we have different samples. Is that okay? So let's set seed so that at least we can get approximately the same. Just a few will have. Let's say our seed is 1, 2, 1, 2, 2. So now we want to simulate 200 observations. We do this 5.98. Did you get the same? So this is better. Okay, let's increase this to 2,000. Oh, so now what do you see happening? I started with 20. We got, I think, 1.64 and then 4.17, right? And then we increased it to 200. We were getting the first one, we got 2.14 and then 5.063. Did you get it? 5.063? Who got this? Did you run the set seed? The first one. Okay. Let's do the 2,000 together. Start by running the set.seed and then that, plot it if the shape looks like that, the histogram, and then we should be getting 2.1045.311. Essentially, as we increase the sample size, our expectation will be that our estimate should get closer to the parameters 2 and 5. And it will not be exact, but generally that's the view. And you can demonstrate that. But remember, this is random sampling. So at a point, maybe 200 may perform better than 2,000. That is why if you are testing this, we don't do one simulation. But you do this over time, and then now we can talk about bias, we can talk about mean square error. So that's the next thing we want to talk about now. Okay, any question on this? Have you been able to run the function and also get your estimate? Okay. Shall we move on? You need to respond so that I know. Other than that, I'm stuck. I don't know whether I should move on or stay. Okay. Please, any question on this? Can I move on? Okay, good. Now, what we want to do, let's do this again. Let's start with 10. So each time, please, we are setting the C to 122 so that we get approximately the same answer. Is that okay? So let's do 10 together. So you highlight all of them like this so that you don't forget to run the set.c. Let's run it. We are supposed to get this. Did everybody get the same? You got the same. Okay. Who got a different answer? Usually, I think it depends on the some versions of the operating system. We get one or two people getting different answers. You got a different answer. What are you using? It's HP, but what Windows? Windows 11. Okay. Yeah, so sometimes we have that. But by principle, if we set the same seed, we are supposed to get the same answer. Or depending on the processor you are using and so forth. Okay. It's not wrong, but as I said, who is using Mac here? Anybody using Mac operating system? Okay, so in some cases, in some of the classes, you realize that if they are using Mac, maybe two people, they will get the same thing, and those of us using Windows will be different. I'm not so sure what really accounts for it, but it could be the way the processes are set. Yeah, but that's why I was asking, because we can have the last about 3 years ago we had an HP issue which was getting different answers from all the classes, even though the person said it. I won't mind it. Yeah. If I want you to, but this is to help you to, for example, if at a point I was writing a book and then I stopped along the way. But if I want you to get the same, if you are following the book, I expect you to get the same thing. So I put in Z.C so that it helps you to get almost a similar graph to help you. But just to caution you that there are instances where, depending on the computer you are using, you will get different results than what is in the Z.C. Okay. Can we, so we've seen 10, right? And we all got the same answer. Good. Let's increase it to 100. And then we are going to rerun everything. Now it's 2.8, 7.3. So you see, the 10 is doing better than the 100. Okay. So we increase it to 1,000. Now, what statistical principle are we trying to illustrate here? We are doing the law of large numbers. Checking it empirically. Is that okay? So now we increase it to 1,000. Now it's a bit better. We are getting closer to 2 and what? 5. Let's change it to 10,000. And of course, set the seed so that okay, it's getting even closer, right? We can go to 1 million. And as we increase the sample size, what happens? We get closer to, and this is what you were 200, right? Level 200. Start 221 also, or 224, 221, 224. So that's the law, weak law of large numbers. As you increase the sample size, you expect your estimator to approach the population parameter, and that's what we are demonstrating. This is everybody okay with this? Okay. What I'm going to do now is that I want us to now find the bias and the mean square error. Now, how are you finding the bias and mean square error? In star 333.
Bias. For bias, you find the
of the parameter.
So when it's equal to the parameter, then it's on bias.
Okay.
When it's on the other else, then it's bias.
Okay. Now, how do we now demonstrate or find bias in now? What do you think we should do in order to find bias and mean square error? In 333, you were finding this theoretically, isn't it? How were you finding it? Good. Okay, so what is expectation?
What is expectation?
Yes. That's why I said in programming you have to think from the basis. Yeah, so what is expectation? 112, you know what expectation is. What is expectation? In a layman's terms, what is expectation? Is that mean, isn't it? Good, okay. Now, if you are finding bias, the expectation you are finding is in respect to what? It's the estimator, not a sample, right? Okay, so how do we now find this? Well, last week you were finding integral when I came here. So if you know the distribution of the estimator, then you can now do the theta hat. The expected value of theta hat will now be what? Let's say the integral of theta times what? F theta hat, right? Is everybody okay with that? So you can do that way as well, but that will be too tedious to do. Okay, so essentially we can treat this as finding the mean of the estimator. Now how do I find the mean of the estimator? I come to basic principle. It means I can add all of them and divide by the total number. That's the basic principle of finding a mean. Okay. So how do I do this? In finding the bias, it means I will repeatedly sample from this distribution. Each time I'll find the estimates. I do so a large number of times. So if I do it 1,000 times, I'm going to get the same parameter. How many? 1,000. The rate parameter, I'm also going to get what? 1,000, right? Okay. Then what do? I find the mean, I subtract the parameter from it, and that gives me the bias. Is everybody okay with this? Oh, thank you. Please, is everybody okay with this? That's what empirically we call a bias, just like you were doing in 333. Is everybody okay? Alright. So now how do you do this? Well, you see this sample, I can have two ways. We can sample each time and calculate our method of movement, or I can also generate a data set like a matrix in which each row is a data set, and then I apply my function to each row. Then I get a 2 by, let's say a 2 by 1,000 matrix made up of shape and scale estimates. So it depends on how you want to approach it. We'll go through the matrix principle, which is that we're going to get a matrix like this, where we will have n columns, which means each sample will have what? N. So let's say sample size 10. Then it means we have 10 columns. So if I take, this is sample 1, this is sample 2, until we get to sample what? R. Is that okay? Then each of them, I'm going to calculate my shape and scale parameter. Shape and scale parameter. So at the end of the day, I'm going to get a matrix made up of what? 2 columns and what? R rows. Each R row is what? The estimate. Now from these estimates, I can find the mean for each column, and then I subtract. So the first one is the shape. I find the mean, I subtract 2 from it, that gives me the bias. And then the mean square error, I can also find the variance of it, and that gives me the mean square error. And the other one, I can now find it like that. Okay, so is everybody okay with this? Please, is everybody okay with the illustration? Okay, so let's do so. We're going to use a simple sample so that it will be easier for everybody to understand, or we can display it for you to see. So computing bias and MSE. Okay, so I call this data sim, and I'm going to use a function called apply. Okay, we have the apply family of functions. Please, you can go to the YouTube. If you check the page, search through it. I've done the apply family of functions. Just, I think, about 40 minutes or so. Take your time and practice through. That will help you. So I'm going to use the apply function here. So apply. Then I'm going to use this. So 1 to R. So R depends. For a start, let's just use 5. But we have to, if we are calculating bias, we need to do about more than 1,000. But I want us to know how this is done. So function, and actually I'm not going to, it's not even necessary to do anything. I'm just going to put what we have here in there. Let me, so please, n is 10 like this. Okay, so if I want, and this is how you program, you don't want to be going to your function to be changing things, so you do it outside and then you pass the names into the function. So in that case, oh sorry, it should be shape, right? So, and then what? Rate. You see I've changed the caps to caps so that it will be different from what, let's say, R stores it in there. What I don't want to is to be going in. If I want to change the shape to 10, I have to interact with my function. No, but I can just do it outside and the function remains the same. Okay, so that's how you program so that you don't. So let's see how this looks like. Okay, now so data sim, I can come here and check data sim. So if you look at it, it's what? A 10 by what? 5 matrix. Each row is what? Each row, no, this one, each column is what? Each column is a sample. Yeah. In the example, I can also do so by transposing it. If I want it to be the warehouse, but it doesn't matter whether it's in row or columns, you'll get the same thing. So we shouldn't worry. But if I put all of them inside the T function, which is transpose, it will turn it, and then each row will be a sample, and then the columns will be what? The repetitions. Okay, please, is everybody okay? And we can display it. So if we display this one, if there it is. So these are the values. So so the first one is sample 1, the next one is sample 2, the next one is sample 3, and so forth. Please, is everybody okay with this? Okay, have you been able to do it? Now, what is happening here is that I just want something to help me simulate or generate random samples from a gamma with these parameters, but repeatedly. Okay, so I took just a sample of 5. That's why the columns are 5. And each column must have a sample size of what? 10. Is everybody okay? Can we move on? There's nothing there. Okay. So those are the parameters we need in running that. So we want R 5 repetitions. The sample size should be 10. The shape we are looking at is 2, and then the rate is what? 5. Okay. Now, it means that if we want to proceed, we now want to find estimates for each of the 5 data sets. And they are in column wise, right? So I also need another function that will help me to apply this to each column. And to do that, I'll use the apply function. And 2 means each column, so I'll apply our function we wrote earlier. So here, our comment is generate a sample of size n and repeat R times. Well, the next thing is that we organize it in a matrix form, something like that. So that's what that code does. We generate sample size in a matrix form, and then we put them in a matrix form. Next is that we compute the estimates for shape and rate for each sample. So how do I do that? Well, I'll call this data, so I'll use the apply function. Please, when you go, take time and watch and practice through what I have said. So here, I only call the function we wrote. The function was what? momgam. So what this means is that take each column. So each column will be passed to the mom gamma as well as a data set, and that's what actually we've done. So at the end of the day, we are going to get 2 estimates for each of these 5 repetitions. So if I display this, you see I have shape and rate how many times? 5 times. So the first row is the shape, the second row is what? The rate. And these are estimates. So now I'm in a position now to find what? Bias, and I'm in a position to find what? Mean square error. So that's the sort of thing you were doing in STAR 333. Please, if you have any question, please ask. Okay. Are you done? Not yet. If you are doing A or in B or in place, there's Mavis Beacon. You must do so before you leave here. Otherwise, when you go to the workplace, they give you, and then you are looking for A and B. It's not nice. Or you go and do your master's, and it reminds me of one of my mates. But he was an old man, so he used to write because he couldn't keep up with the way the professor was typing. And then there are no time for you. Okay, can we move on? Okay, so display your estimates. So you see the first one, the shape is 2.4. The next one, my own is down 1.49. What am I expecting? I expect it to be 2, right? So if I find the mean of all this and I subtract 2 from it, it gives me what? It gives me the bias. Okay. So to find this, I need to also write a function to compute what? Bias. And I'll write another function to compute what? Mean squared. Okay. So instead of those theoretical stuff that you are doing, now we are reducing everything to what? A sort of a program that does that. So let's write the bias function. How should this function look like? So we'll call it bias dot fun. What should be the form of this function? What arguments will this function take in? And what will be the output? Yes.
Take the mean of.
Is the mean? It will take the mean. How will it take the mean?
Write the function that will have. Divide by the thing.
So what do you need? What do you need in the function to help you compute the bias? That's what we. The basic, it means it's either a bit or something.
So you need a test.
It needs what? Okay, we need the estimator. What again? We will need. Good. Okay, so the key thing is that you need the parameter. You need also the estimates of the parameter in that function. Is everybody okay with this? Then we will find the mean of the estimate. We subtract the parameter from it. Okay, so some of this, as I said, you have to think from the basis. What do you need to do this? That's what you pass to the function. What is the output? This is what I want. Okay. So it will be a function that takes in, let's say, theta hat, theta dot hat, and then what? Theta. Is that okay? So if that is the case, we are going to find mean of what? Theta hat. Then we subtract what from it? Theta. Is everybody okay with this? So that should give us the bias. If it is negative, what does it mean? When it is 0, what does it mean? When it is negative, what does it mean? It's bias. Yes, it's bias, but you have not described it fully. Yes. Yes. It is underestimating the parameter. Good. And if it is positive, overestimate. Okay, good. That's nice. Okay, what else? We need mean square error as well. How can we compute the mean square error? So usually when I write this function, I put them together, because the mean square error, what will be the argument for that function? What will be the argument for the mean square error? So you see the mean square error of the now we're going to compute our mean square error as the number of repetitions, right? Our theta hat I minus theta all squared, and of course I will move from 1 to r. So this will compute our mean square error for us. Is that okay? Alright. So how do I write this? What do I need in order to, or what will be the arguments of this function? We need what and what? The mean. Mean is not it's a statistic. We need theta hat and theta. Of course, you need the estimates as well as what? The parameter. So it's the same as that of the bias, right? Okay. Do you want us to write a separate function, or we should put them together? Okay. So we can combine them. If we want to combine them, then I need to come here now, put them in what? In curly brackets. But if it was just one, I could have just left it on the line and it will compute it. Okay, so if that is the case, please, if you are not following, you need to draw my attention. Whatever it is, you do this in your exam. And it is important that you understand this if you want to work as an actuary, because this is what you use in estimating all this. And we are doing this because it will now help you to understand all the other packages. Whatever we are doing here, we could have just called a function in how to do it. But I'm taking my time to go through the basic principles so that you understand this concept in order to build upon it. So please make sure you understand. If you are unable to do this, I'll meet you next year. God willing. That one is non-negotiable. Then when you can become my class rep, because you already know what you will be doing. Okay. So that's the bias, right? Now what about the mean square error? Can we get somebody to help us? How can we write how should we compute the mean square error from what I have written on the board? Yes. Please hurry up. I need time. I have to go and print your questions. So hurry up. S apply. Why S apply? This one. How can we compute this in That's what I'm saying, that when you want to program, you have to understand this from basic principle. Don't look at the formula. Just break it down into what have I written here? Here. If you want to find it, what are you going to do? We can set the R. Okay, yes. Yes. And square it. Okay, that's one way. What other way? What would be a simplified form for what he said? Did you hear what he said? Okay, please come again. Speak up so that they can.
So I'm saying that we can set our R value.
In order, what will be the R in this function? From what we are doing, what will be R?
Like the number of.
How will you find R? Yes.
He said it was like a repetition.
Okay, good. Assuming you don't know that I have set it up there, how would you find it within the function?
So you can assume that
This one is one assumption. You don't need to assume.
like the length.
Exactly, yeah. So it will be the length of the theta hat. Is that okay? Because theta is just one value, or maybe two. Yeah. Yes. Can we?
So since I was saying,
I'm not sure they hear you. Can you hear him?
so now we have.
Can you hear him?
So now we've set our R.
Yes.
You can now write a function by following what we see on the board.
Yes.
So we have 1 divided by R times the sum of the parentheses squared.
The sum. How would you write that? Sum and parentheses.
So sum is bracket. Theta has
Which bracket?
the normal bracket. So
Which one is the normal bracket?
that's the normal before.
The sum. So it's parentheses. Okay. All right. Okay. And then we square it. So that's right. What will be the simplified form? We've been saying this all morning. If I divide this by R, what am I calculating? I mean, so instead of doing sum, we could also just find the mean of the deviation squared. That's it. Is that okay? Please, is everybody okay with this? Yeah, so that's what we will use. Okay. So the mean square error will just be mean of theta dot hat minus what? Theta. And we need to square what is inside. So to be on the safer side, just put this one there. So that is the mean of what? The deviation square. Is everybody okay with this? So that's basically the mean square error. And so don't. There was a question that one of our, I have forgotten it. When I get it, I'll ask. It's years ago. So I think it was a kite. No. So I've said the answer. But I think it was rectangle or so. And then you are supposed to join the points together without lifting the pen. So what we saw is that time with that Markov chains and so forth and transition, probably we were thinking about using these two. But if you give it to a small boy at kindergarten, they will join it with a kite and they will. So what is the motive? We couldn't do it, and the reason is that when you are trying to solve a problem, you don't look at it from the basis, you look at it from the top. Yeah, so that's it. So if you are programming, when you see a problem, a big problem, just look at it from basis. What is the principle in doing this? And you will be able to do it quite easily. Okay, so now what do we return? We can also use a tab, and then we call buyers and what? MSE. And then I can look at names, which is the same as what we did. Do you want, if you want to if you want to round them off to some decimal places, you can, isn't it? We've done that already, so we don't want to. All right. So that's it with this function. Right. So this function should take in any. So maybe we have to call it bias MSE, right? Because whenever you name a function, it must give you an indication of what it is actually computing. Other than that, you come back to it 2 years later and you won't even know what, sometime in a week. Especially if you are having let's say a program that runs on so much. So I can show you some. So this is like some work that we are doing. And you see, this is not even long, but it's 285 codes, right? This is another one. So let's see. So in order for me to get my results, I need to run 500 and something. Okay, so you can't afford to be naming a function X, and then you have to now go in and check whether what X is doing. Do you know what I'm saying? Yeah, so the name should reflect what, let's say, the output, and it becomes easier for you to relate to it. Or sometimes you share the program with another person. You don't want the person to be calling you back or sending email back and forth. What is this? So usually you have you comment as well in there. So you see this one, I said plot of bias. So my collaborator will get it and know that we are actually plotting bias over here. If you come here, we are plotting MSE, something like that. Okay, so comment and also naming of objects are also important in programming. It makes life easier. Okay, so now let's move on. So we need to run this at first to make sure that it works. There's no error, which means the function, if we go to environment, we should see that function there. It is called what? Bias sim. Bias MSE, and that's where we have it. So once we have it in our environment, it means we are good to go. We can use it. What we need to know that we see, if we want to use this one, remember this one is what? A matrix. So it means we can also use the apply and now on each row, right? Is that okay? So if I apply this one on each row, I'm going to get it. Or alternatively, I call bias fun. So they are, let's say, for the first one will be theta. Okay, so theta hat. So if I want to find that of the shape, it means theta hat will be this one, right? So I can comment here shape parameter. So if we want to get the shape parameter, then this one we need to select what? The first row, right? So it will be like that. You remember subscripting? Yeah, so that's important. And then theta will be equal to what? Do you remember? So here, what is what? The big shape. Is that okay? Please, are you following? Okay, so we do this. And so the bias is 0.333, MSE is what? 0.712. Okay. Now in itself, it's not really bias MSE. If you calculate an estimator and you give us the bias in MSE, all we can say is that how close is it to 0? So if you are using one estimator, virtually there is no need to be calculating bias in MSE. It only becomes relevant if I have two, because then that will help me in choosing which one is the best. Is that okay? Yeah. Okay, so that's for the shape parameter. And Similarly, we can get that of what? The rate, and the rate parameter we need to put here as what? Rate, and over here should be what? 2. And then we run it. So that of, and this is understandable. The shape was 2, so its magnitude is a bit smaller than that of what? The rate. The rate was 5. So you see that the MSE is quite big. And you could see that as well from the values we got. How close are they to 2 and how close are they to 1? Okay. Any question? Any question on this? Okay. Now, moment estimator is always simple. What we have done is, it's like we could have left this for you as an application, because the only thing we've seen over here is that you make use of functions. So once you know the principle, the rest is just functions. Okay. Now, in the case of the MLE, we are not going to, we have to now go back to the principle, and then we see its implementation in R. So in MLE, what is the principle? Maximum likelihood estimation. What principle do we use there? We talk about the regularity conditions. What are they? My dear friends, Dr. Issa's door is just here. Okay, so, but the key thing in the key principle in MLE is what? If I have a data, what does the maximum likelihood principle state? If I say it comes from this distribution, so you see, the key thing there is that if I have a data set and I want to check whether it fits this distribution, all what I'm saying is that because in maximum likelihood you must decide on which distribution fits it, but you are not done. You need to calculate the parameters. MLE helps us calculate estimate of the parameter. So the principle is that if I have this data, then the values of the parameter, okay, that gives me the most likely outcome to generate that data is the estimate. Is that okay? So we are going to use the same principle. So in other words, in 333, if I were to ask you what is the MLE for the exponential distribution, you will be able to tell me. What about this one? The Poisson distribution. What is the MLE for the lambda? It's x bar. It's the same as well, the moment. Is that okay? But because of that principle of generating that data, we don't just calculate the mean as the MLE. Is everybody okay with this? Yes. We need to go back, write the likelihood function the same way you were doing. You write the likelihood function, then we are saying how well does this produce this data. So I'll run my likelihood function on the data and optimize it, and that's how MLE is done. So if it goes back to optimization, so all the optimization methods you need, Newton, graph sense, secant method, what have you, comes in finding the zeros of that function. So that's the sort of principle we'll use. So we have the data, we have an estimator, we have a data, we assume that, or we want to check whether it comes from this distribution. we will write our likelihood function for that distribution based on the data, because your likelihood function is on the data, and then we'll take our likelihood function and we'll optimize it on the data set. That's the sort of thing we'll be doing. Is everybody okay with this? Okay. So I have a recording on this on the YouTube page. I want you to go through, take your time and listen, but the principle is what I have done. So whatever we are doing, we will write a likelihood function. And to write a likelihood function, remember that your likelihood is just what? What is your likelihood function? It's what? The likelihood is not the log. What is the likelihood function? And what is that one? What is the multiplication? It is what? It is a... Yes. So the likelihood is a joint PDF. And why do we have the product? Good. Yeah. So you have to do all this basic stuff. And once you know that, you don't really memorize things on your, that's why most of you drill in star 333. Instead of you to understand the principle, you are always looking for questions and answers. Okay. And then when Dr. Isa trick is bored, then we have a problem. Yeah, so the likelihood is a joint distribution. But we assume that each of the x's comes from the same distribution as well, right? And they are independent. So we're able to write it in that format. Okay. And then you said log likelihood. Why do we use the log likelihood? Why do we usually maximize the log likelihood and not the likelihood? When I used to teach 333, I used to ask this all the time. Yes. Why? Yes. It's not easy to differentiate. That may be one of the reasons, but there's a key reason why we use the likelihood. That one is, it helps you, yes, but there's a key one. Okay, so the key thing is that, remember in the likelihood, you want to find the maximum point, right, of the function, right? Is that okay? Yeah, so because the log is also, when we find the log, any value that will maximize the log likelihood function also maximizes the likelihood function. So that's the key thing. In other words, the log likelihood is easy as he's saying, but the key thing is that whatever value will maximize the log likelihood automatically maximizes the likelihood function. And similarly, if it is minimization, it will minimize the likelihood function. So that's the key thing you use. Okay. Now, so if I have, let's say, the likelihood of this one, what is the log likelihood? So that is going to be, remember, we are going to sum n times, right? So we are going to get, so sigma x, lambda sigma x, right? And then minus n lambda. Are you following? Is it? Yeah, because this one will be negative lambda. We sum it n times. We are going to get what? Negative n lambda. Then minus 1. Because that is 1 over that, we will get sigma x factorial, right? So xi factorial. All these are 1 to n, sigma 1 to n. What will be your score function? My dear friends, let's move on. Anyway, but you agree that we can take this one off.
Yes.
Why is it so? Yeah, because it doesn't have anything to do with what? It doesn't have lambda. So when we differentiate, that part will be what? 0. So as a matter of fact, we can just use this as our likelihood function. That part. So what is going to happen is that in R, we have to write this function as our likelihood function, and then we optimize this based on the data. Okay. And this we can easily write this function. So that function will take in x and what? Lambda. Is that okay? And that's 1 + 4 of maximum likelihood. We don't know lambda. If we know lambda, we won't be here. But the function already involves what is unknown. So when you are doing this, you need to provide a starting point. In other words, you must provide a value for the lambda before we can optimize it to get to the position. So maximum likelihood is like a search algorithm. That's why we use those optimization methods. So you start from a point, and it will iterate based on the data to reach the solution. And the solution we hope to get to what? The estimate. That's the idea in here. So it's quite not that difficult, but if you understand the principle, that's it. So usually when you are doing this, you can use, because the moment estimator is easy to find, you can always, the starting point can be what? The moment estimator. That one gives you some idea that it will be closer to the parameter, sort of, and then you optimize it. And how do we do the optimization in R? There are several routines. The basic one is called optim. So you can, if you do question mark optim, so you can pass this function and the data through it, and then it will optimize it and give you the estimate as well as the standard errors, and even the facial information and all those things you were doing in 333. So that's the sort of thing we have to do in order to do maximum likelihood. So get your likelihood function. Another way around, if you don't want to write the likelihood in this way, then remember that this likelihood, right, of this can also be written as I moving from 1 to f xi, right, like that, isn't it? Which means you remember what we talked about. For every function we have the f, and f is d. F, so for example, ds, d Poisson, and so forth. So instead of writing the likelihood function this way, I can also just write what? ds or d Poisson, and then I pass in the data. So that's easy, but the pitfall of it is that if you have a distribution that is not already enough, you cannot use that one. It means that you have to go through the basic principle. Or maybe if you have a mixture, I know start 331, you talk about mixture distributions, right? Are you sure? Maybe, now we don't. But you know what a mixture distribution is. I can combine two distributions, and then it becomes a mixture distribution. So I can combine, let's say, exponential and a gamma distribution. That's why sometimes when you have a data set, you realize that they have let's say, if you plot a histogram, one part follows like an exponential distribution, the other part follows like a normal. In other words, it may have different local maximums and so forth. So that signifies that it comes from two distributions. Maybe those on the right, yeah, it's like an income distribution. So if you take, let's say you come to the university and you take senior members and let's say junior members, or you go to a private sector, you realize that among the senior members, they will be on the right because they get higher salaries. The junior members will be on the left, and the salary distribution will be different, what is here from the other one. So if you want to fit a distribution, you cannot fit one. You can actually combine two, and that's what we call the distribution. Okay, so let's meet you next week, okay? Fantastic. Take tomorrow's lecture period to go through the maximum likelihood.
Okay, let's do this.
Yes. Or maybe you should come for tutorial.